My name is Yulia. I'm going to present millimeter wave data networking for autonomous vehicle systems. The use of the millimeter wave spectrum allows for high throughput and ultra-low latency applications. However, the signal propagation in the millimeter wave band suffers from more degradation compared to the sub-6 GHz band, such as higher attenuation due to path loss and also higher sensitivity to blockage. We typically need for higher directionality in transmissions. However, for multicast applications, such directional transmissions pose more challenge, such as higher number of hops and therefore higher traffic loading within the network. We therefore propose infrastructure-aided millimeter wave multicast dissemination algorithm, which we call RAMDA, and for comparison purpose, we also develop vehicle-to-vehicle millimeter wave dissemination algorithm, which we call V2VDA. The following are contributions of our study. We designed a system that achieves ultra-low latency for critical messages and also high throughput for non-critical messages. We developed RSU-aided millimeter wave networking scheme that jointly uses wireless V2I and V2V transmissions as well as transmissions over infrastructure backbone using point-to-point links. We develop routing algorithm for both schemes and FDMA TDMA-based scheduling schemes that properly allocate resource for different types of links considering cross-layer MAC-PHY parameters. We find that the RAMDA scheme has significantly better delay performance than V2VDA scheme. On the other hand, RAMDA's throughput capacity level is as high as that of V2VDA. Following is the scenario that we consider. Source vehicles on the highway generate packet flows that is to be disseminated to all vehicles within a specified dissemination span. For example, disseminated to all vehicles within 1 kilometer from each source vehicle. The objectives of our schemes are as follows. We would like to maximize aggregate data throughput capacity of the system, and also ensure that the 95th percentile delay requirement of the packet is satisfied. We now move on to the network systems and architecture, and this figure illustrates our network systems. We have vehicles traveling on the highway, and we also have RSUs as part of the infrastructure. Our data networking schemes employ highly directional transmissions, and there are several types of such transmissions. The first is intralane transmission. As illustrated here, we have the green arrows and we also have the red arrows. Intralane transmission is transmission between vehicles located on the same lane. We also have uplink transmission, which is transmission from a vehicle to RSU. We also have RSU to RSU transmission over point-to-point link on the infrastructure backbone. We also have downlink transmission from RSU to vehicle. We also have interlane transmission, which takes place between vehicles located on adjacent lanes. The following are the network parameters that we consider. We consider inter-vehicle distance. We also consider inter-RSU distance, which is distance between RSUs. We also consider antenna beam width level, which ranges from 5 degrees to 90 degrees. And for illustrative purpose, we use 10 degrees. We also consider transmit power level used by vehicle and RSUs. We also consider spectral efficiency of data links, TDMA spatial reuse factor for scheduling, and also beam alignment overhead as a result of using directional transmission. For illustrative purpose, our data networking schemes operate on the 60 GHz band. Now moving on to the network architecture for RAMDA. So each vehicle traveling on the highway will associate to the RSU with which it has the best communication quality. For example, this vehicle associates to this RSU and this vehicle associates to this RSU. So the vehicle that associates to RSU becomes a client of the RSU. Among the clients of each RSU, the RSU selects the vehicle with which it has the best millimeter wave communication quality. And this is typically the vehicle which is nearest to the RSU. For example, this RSU selects this vehicle as its V2I gateway relay. And this RSU selects this vehicle as a V2I gateway relay. And this V2I gateway relay will later on facilitate uplink and downlink transmissions taking place within each RSU cell. Furthermore, each vehicle also, through signal monitoring, find out the vehicle on adjacent lane with which it has the best communication quality. And this is typically the vehicle which is nearest to the vehicle on adjacent lane. Now moving on to the network protocol of RAMDA. Let us now consider source vehicle residing within the cell of RSU2. For example, this source vehicle, if it wants to disseminate packet over dissemination span in this direction and in this direction, this is how the protocol works. This source vehicle will transmit on a hop-by-hop basis intralink to all vehicles located within the same RSU cell. The V2I gateway relay will then receive packets from source vehicles located within the same cell on the same lane. The V2I gateway relay forwards such intralink packets to the RSU associated with. The RSU will then forward the packet to neighboring RSUs that overall cover the dissemination span. Each RSU then forward downlink the packet to its V2I gateway relay on each lane, and the V2I gateway relay will forward on a hop-by-hop basis intralink to all vehicles within the same cell. In addition, each vehicle also forwards to the vehicle on another lane any received packet, such that now all vehicles within the dissemination span have received the packet originating from source vehicles within this RSU cell. For V2VDA, the networking protocol is simpler. It does not involve the use of RSU infrastructure, so each source vehicle transmits on a hop-by-hop basis to all vehicles within the dissemination span. Each vehicle also transmits any packet to the vehicle on adjacent lane. And now we move on to RAMDA'S FDMA TDMA-based scheduling and resource allocation. We allocate resource for the different types of link in FDMA basis and also TDMA basis. We allocate on FDMA basis resource for data links in transmit and receive directions. For example, for intralink transmissions in forward direction and intralink transmissions in backward directions. And also resource for uplink direction and also resource for downlink directions. On the other hand, we allocate resource on time division basis for transmissions occurring in the same direction. For example, between neighboring intralink transmissions and also between neighboring uplink transmissions or between neighboring downlink transmissions. We employ common spectrum for transmissions done in different non-overlapping directions. For example, between intralink transmission and V2I transmissions. These transmissions experience little to no interference to one another due to high directionality in transmissions. The following slide shows our approach in resource allocation. Our goal is to maximize the system's throughput capacity, and we do that by maximizing the throughput capacity of the link which has minimum throughput capacity. In short, we want to maximize the bottleneck link throughput capacity. We find the analytical expressions to allocate such resources to different types of links. We consider two performance metrics for our networking schemes. The first is throughput and second is end-to-end delay. The throughput capacity of the RAMDA'S system can be expressed as follows, and the system can be loaded at a factor of rho less than 1, such that the throughput of the system is equal to rho times aggregate throughput capacity of the system. The aggregate throughput capacity of the V2VDA system is formulated in a similar approach as the RAMDA'S system. Ultimately, now we have to ensure that end-to-end packet delay performance is guaranteed. We denote as DP the 95 percentile end-to-end packet delay, and the 95 percentile end-to-end packet delay consists of two components. The first is the 95 percentile waiting time, denoted as WP, and the other one is the end-to-end packet transmission time, which is denoted as TTX. We would like to find out the maximum realized critical message throughput that satisfies the 95 percentile delay requirement. Using the bandwidth allocation method that we have seen earlier, flow admission control pacing mechanism can be implemented such that packets are not fed into the system at a rate faster than certain level. So the waiting time at non-source nodes or intermediate nodes is effectively zero or can be deterministically bounded. Therefore, we approximate just waiting time at source node using MM1 queuing model. The service rate we use is equal to the throughput capacity per vehicle, and the arrival rate of packets on source nodes depends on the traffic loading to the system. The transmission time of the packet is computed from the time packet is being transmitted by source node until the packet reaches the farthest vehicle within the dissemination span. We have verified by simulation that our analytical models are accurate by about 5% for throughput capacity, and for the 95 percentile delay metric, our simulation confirms that our analytical model serves as upper bound due to use of MM1 queuing model, and the ratio of simulation to analytical delay performance is equal to 1 to 2.5. The following slide shows the delay throughput performance behavior of both V2VDA and RAMDA'S scheme. The red curve shows the performance behavior of V2VDA scheme, while the blue curve shows the performance behavior of the RAMDA'S scheme. We see over here that the RAMDA'S scheme can achieve similar throughput capacity level as V2VDA scheme, and the reason is as follows. The RAMDA'S scheme's total bandwidth is dominated by the total required intralink bandwidth. On the other hand, the rate of data traffic to be forwarded using V2V intralink is similar between the RAMDA'S scheme and the V2VDA scheme, therefore causing their throughput capacity levels to be similar. When we look at the inset here, we see that when we consider very strict latency requirement in the order of 1 milliseconds, the V2VDA scheme has a realized critical message throughput of about 1.9 gigabit per second. On the other hand, when we consider sufficiently high RSU density, such as the RSU 50 meters, the realized critical message throughput is about 2.4 gigabit per second. This shows that when the RAMDA scheme has sufficiently high RSU density, RAMDA has better delay performance than V2VDA. On the other hand, by using RAMDA, we are not sacrificing the overall system's capacity to serve non-critical message when using the residual capacity of the system after serving critical messages, as we can see from the similar throughput capacity levels of both schemes. The reason why the RAMDA scheme has better delay performance than the V2VDA scheme when we have sufficiently high RSU density is because RAMDA significantly reduces the number of V2V hops to be traversed by each packet to reach the whole dissemination span. In conclusion, we have developed RSU-aided and V2V millimeter wave dissemination schemes. We developed routing algorithms for both schemes as well as FDMA TOMA-based scheduling mechanism that determine the sizing of resource allocations for both schemes. We develop analytical models for the delay throughput performance of both schemes and verify them by simulation. We find that using RAMDA with sufficiently high RSU density achieves more superior delay performance than V2VDA, especially when considering very strict latency requirement, let's say in the order of 1 millisecond. On the other hand, the throughput capacity levels for both schemes are similar. Thus, using RAMDA to support critical message does not compromise the overall system's ability to handle non-critical messages at high throughput rate. Thank you.